Alright, so today what we want to do is we want to go over right now vorticity and basically the vortex transport equation. So one of the first things is just a quick reminder on what is vorticity. If you remember, we had this defined before, and vorticity is basically just the curl of the velocity field. So we can define it simply as omega equal to del cross u, where vorticity is a vector quantity. Physically, what is vorticity? Vorticity is twice the angular momentum. And one quick identity that we can write down is that we do know also that what is called the solenoidal condition which says that the divergence of the vorticity field is 0. So and this comes straight from we can get this from a vector identity that you proved in homework 2. Basically, if you look at it, this is just del dot del cross u, which is 0 for any vector quantity u, regardless if it's velocity or anything else. So what does this mean is our solenoidal condition is basically similar to our incompressible flow condition for the velocity field, the only difference being that it actually adheres to, is always valid and always should apply. The next component that we want to do though now is we want to take our general vorticity, derive our general vorticity transport equation. So to do this, what we're going to do is we are going to we'll start with the incompressible Navier-Stokes equations. We'll do this for an incompressible flow. You can also do this for a compressible flow, but we won't do that now. So if we have our incompressible flow, so du ut, we'll use vector notation for this, plus so our time rate of change of the velocity field plus the advection of the velocity field is equal to minus 1 over rho gradient of the pressure field plus gradient of a potential field, this would be our gravity, plus kinematic viscosity times the second derivative of the Laplacian of the velocity field. Right? So our viscous term, so we have our viscous term, we have our, in this case we have our potential function, so where is a potential function that represents our body forces. So now what we want to do is if we think of our definition of vorticity, well, before we do that, let's rewrite some of these terms. So let's rewrite the advection term. So the advection term, which is just, we've written it out here, is just u dot del u We can use a little bit of our vector identities again, some of these from homework number 2, or also ones that you can look up in a book like Eris, or some of the others. So this can be written as 1/2 del u dot u minus u cross del cross u. Or we can say that u dot del u is equal to 1/2 del times, or del of u, it's a gradient operator of u dotted with itself, minus u, and then we recognize here, what is this? Alright, this is our vorticity, so this is just u, the velocity field, crossed with the vorticity vector. So with this, we can now basically put this back into the Navier-Stokes equations, and so we can rewrite our Navier-Stokes as now du dt plus 1/2 gradient of the u velocity vector dotted with itself, basically squared, minus cross product between the velocity and the vorticity vectors, equal to minus 1/2 rho gradient of our pressure field plus gradient of our potential field plus kinematic viscosity, some second derivative of the velocity vector. Now we want to turn this into a vorticity transport equation. So what do we need to do if we want to do that? Well, we just need to use our definition of vorticity that we have up here at the top. That we have up here. So basically all we got to do is just take the curl of the Navier-Stokes equations. We take the curl of the Navier-Stokes equations, terms like this will turn into vorticity, right, in a very straightforward manner. So let's take the curl of the above equation. If we do that, we have now del, or our gradient operator, crossed with du dt plus, again, curl of 1/2 gradient of u squared minus curl of our cross product between our velocity vector and our vorticity vector, and this is equal to minus curl of 1/rho gradient of our pressure plus the curl of the gradient of our potential field, plus we'll have one more term here, which we'll write down over here, which is going to be the curl of our basically our viscosity term. And now let's give each of these terms a different number, because we're going to go through these one at a time. We'll call this term 1. We'll call this we're having a little technical difficulties now. Alright, so let's see if we can go back to looking at this. This will be term 2, term 3. Our pressure will be term 4. Our potential field curl will be term 5, and curl of our viscosity will be term 6. All right.